Hello everyone, and today we're going to be talking about an addendum. So we're going to be looking at off-the-shelf solvers and model predictive control. So we're still solving the same control problem that we were talking about earlier, but now we can use different nonlinear optimizers to solve for things with nonlinear dynamics, as well as with control constraints. So that's the one thing we talked about. We have this LQR problem, but if you look at it, this k times x, there's no bounds on what you can take. So practically when you're working on a robot, your robot can only apply so much force. So how do we encode these constraints? One way we can do this is through constraint optimization. So what we're going to do is specify some input to polytopes. A polytope is a geometric object with flat sides. So we can constrain things like this. And essentially what we're saying is that some matrix times our vector x has to be less than some value b, which is also a vector. So we can iteratively construct these polytopes. So what you'll get up is something like this. Based on this line, it has to be less than it. So you get this area. And then, so we can draw a second line in here, and then say it has to be above this line. So now we constrain it to this position of the state space. Then we can add a third line and constrain it to this position of the state space. So all we've done is essentially apply some constraints like we talked about in week 4. We're trying to find some control which minimizes our cost function subject to these constraints, and these constraints are constructed so that our controls have to be contained inside this geometric shape. And we can define this in such a way like we have some U0, so like your left wheel control and your right wheel control, U1, saying that these two controls must maintain inside this. So I can only have certain values of U1 and only certain values of U0. So we can write our original optimal control problem again. So if you remember this, we had this form, so these two terms, and we can add in additional terms that are linear. And then we write our dynamics as some constraints, and then we have our additional constraints based on our input polytopes, so saying that our control must satisfy this constraint as well. And then what we can do is we can apply some solvers, and these solvers will use non-quadratic optimization techniques in order to find our control without really doing any of that mathematical theory behind the LQR. We're not going to be talking about these general solvers, but they exist out there, and a lot of people use them for this exact reason, because you don't have to worry so much about exactly what's happening under the scenes usually. A lot of times, if you have a good problem formulation, they'll just kind of work. So what are some of the drawbacks? So they can be especially slow. Since we aren't using some structure of our problem, for really complicated controls problems, these can take a long time to solve. So these can also fail. You're not guaranteed to succeed. So depending on your problem definition, you might find a solution that is infeasible or doesn't satisfy your constraints, and they'll just fail. And this doesn't give us a feedback policy. It only gives us that open loop control. Remember, that's when I figure out what my control should be, close my eyes, and then apply the controls without getting any new sensor information in. So this is great and all, but with that noise that we have in our actual systems, we tend to diverge. So we're going to use this trick called model predictive control, and we're just going to recalculate our control iteratively. So what we do is we start off and we plan our trajectory from t equals 1 to capital T. We execute that control. Then we find our new state x2, and we recompute a trajectory from t equals 2 to t is t plus 1. We're always computing a trajectory of length capital T. And then we're just going to keep iteratively doing this over and over and over again. What you tend to see is something that looks like this. So we've calculated this control going forward, and we're trying to reach this goal position here. So in the first step, we apply the first control, and we get to the position here. And then we recompute our plan. We do the same thing again. We end up at this position, and we recompute our plan. And you do it over and over and over again. And what you tend to see is that model predictive controllers are robust to noise, because every time you're just replanning, you have this inherent feedback that comes through the open loop control policy, just because you're recomputing it over and over and over again. Every time you get a new state, you compute a new plan. That new plan takes into account the realization of the stochasticity that was inherent in the system. And if you do this over and over again, you tend to reach the final goal. So this is the trick that my lab tends to use in a lot of our controls applications, because it works really, really well. So in conclusion, optimization-based motion planning is a powerful technique. Off-the-shelf optimizers can be excellent, but they tend to be a little bit slow on some problems. It just depends on the problem formulation. And constant replanning of model predictive control can turn open loop control sequences into a feedback technique. And the feedback comes through every time you have noise and you get a new state. You use that information next time you compute their trajectory from scratch. Here are some other resources that do a better job of explaining the theory behind what I'm talking about, as well as going into a lot more depth about the math. And this concludes our most mathy section of this course. We started off pretty simply with some linear algebra. We built up all the way to this LQR derivation. I hope you enjoyed it.